but at least we have an equation 8, an equation for fluctuating motion. And there is, as I said, we can use this equation 8 to get Reynolds stress equation, and therefore try to close the RANS equation. That we can do it, but before that, this particular equation 8 forms the basis for what is called a linear stability theory. They do some reduction of terms here, so we are not going in that direction, but you can still take a note of that. So this equation 8, or the last bracketed term here, this is note number 1, I can take this, the last bracketed term vanishes if fluctuations are infinitesimal. So because that only this particular term here, this term has product of fluctuations. If one is small, then small multiplied by small is very small, so it is negligible, and therefore if you are taking your fluctuations as infinitesimal, then this last term is negligible, and if you get rid of it, that 12 unknowns are gone. So this is the foundation for what they call a linear stability theory or stability analysis, by omitting the bracketed term, assuming that fluctuations are infinitesimal. If you do that, you get rid of this particular term, then the equations are closed. At least you have now got one closed equation. Okay, so that's the basis or foundation for this.
Sir,
Yes.
Linear stability theory, if the perturbations are small, why should it be that the derivative of the perturbation should also be small?
Come again?
You said uj multiplied by dou uj by dou xj is small because of small perturbations. But if a perturbation is small, should the derivative of that perturbation should also be small?
Need not be, but you are pushing, you can push this uj prime inside the derivative here, right? You can use the chain rule for products, then it is ui prime uj prime. So it's essentially multiplication of two small terms. So, and therefore that forms the foundation for this, what is called, this is forms the basis or foundation of linear stability theory. Okay, so the last bracketed terms vanishes only when fluctuations are infinitesimal. This is very important for students of turbulence here. That's because first thing, you are going into the linear world, and we have already seen turbulence is a non-linear process. Okay, so you will not gain much by going in this direction, simply because you are getting rid of the Reynolds stresses, right? So by getting rid of the non-linear terms, you are essentially achieving a closed form of equation, which is fine, but this assumes that fluctuations themselves are infinitesimally small. So the way you continue in this so-called linear stability theory is basically, of course, we have, by omitting this. Okay, so the equation 8 becomes closed. Omitting the bracketed term. The 12 unknowns are gone. But then you, the way to proceed here is that in the so-called linear stability theory or other stability analysis, is that you are always assuming a base flow to be a laminar flow. You consider a laminar flow, that means you have some analytical expression for it, and then you assume that fluctuations are infinitesimally small, and then you go ahead and solve this to get some solution. But the only problem is that when fluctuations grow, this theory fails. When fluctuations grow, that's when the flow will go from a laminar to a transitional and turbulent state. So transition to turbulence, when it occurs, when fluctuations grow, it is no longer infinitesimally small, and when fluctuations are not infinitesimally small, your base flow is not laminar, and therefore the theory fails. And therefore I said this direction is not very helpful if you are interested in turbulence. Okay. So for example, if I want to graphically illustrate, let's say you have you are measuring the in a turbulent boundary layer, not in a turbulent boundary, let's say in a boundary layer, if you are measuring some velocity signal, and let's say it is going like this, and suddenly you get some burst of information. Let's say this is the signal. Let's say this is inside your boundary layer, okay, in a boundary layer. In a boundary layer problem. So then this onset here, okay, this particular junction where a turbulent spot is seen, okay, these are called turbulent spots. And this is intermittent. So some turbulence comes and then laminar zone, a turbulence and then a laminar zone. So this signal here up to here, this is intermittent also. This is also called intermittency. And this is completely a transitional zone. So this particular part is called, the flow is experiencing transition, and this is the turbulent part when it has gone into the turbulent condition. And this particular junction where the turbulence kicks in is where you have your critical Reynolds number starting. Okay, so this is your call it subcritical Reynolds number. So this is a subcritical Reynolds number. That means it indicates the Reynolds number at which the flow will go into a transitional regime. You can get this number using stability theory, linear stability theory, in natural transition. Okay, the natural transition means the base flow is laminar. It is free from any free stream turbulence. No background turbulence is allowed. If background turbulence is allowed, then the flow experiences what we call a bypass transition. So this particular subcritical Reynolds number you can achieve it here. So this linear stability theory or analysis, if you solve that equation 8 omitting the nonlinear term, linear stability analysis can give you this subcritical Reynolds number. So the Reynolds number at which the flow will go into a transition regime, but it cannot tell you how the transition occurs later. The process later it cannot tell, because the base flow is no longer laminar. Okay, so once the transition starts, once transition to turbulence starts, fluctuations are no longer infinitesimal. Okay, and the base flow is no longer laminar. So stability theory is not useful here. Stability analysis is not useful. So the takeaway is you can close the equation 8, fluctuating momentum equation, by omitting the nonlinear terms, and you can obtain a subcritical Reynolds number for given problems in natural transition. That means the base flow must be free from any fluctuations at all. It should be completely in laminar state. Okay. You are saying that if I use this particular, if you have access to these three fluctuations and then you are able to compute. Yeah. If you have access to it, yes, you can compute. So you can actually say that these are not extra 6 unknowns. You still have 6, and they go away by closing. Correct. Yes. That will be there. That will be there. Yes. So this will be. It's a good question. So basically, if you have access to ui prime, that means 3 velocity fluctuations, you can compute the velocity gradient here, and therefore this does not constitute 6 extra unknowns here. Okay, only 6 unknowns are there. Correct. So then it will be, but still the equations are not closed. There is a turbulence closure problem. Those things remain. Okay. So now one more takeaway is that here that only valid this stability analysis is only valid for natural transition. That is no free stream turbulence or background turbulence in the base flow, because you are essentially going to start, when you take the equation 8 omitting the bracketed term, you are going to assume this ui bar. Okay, taking, let's say if it's a boundary layer flow, you know the velocity ui bar, or if it's a wake or a jet, you have to assume ui bar flow and then consider a small fluctuation u1 prime, u2 prime, u3 prime, and solve for the equation to see when the system will give you a subcritical Reynolds number. Okay, that is the idea there. So that means you are always considering a base flow ui bar, and that ui bar, of course bar doesn't have any meaning there because it's a laminar flow, but that is constitutes the base flow. And if the base flow has some turbulence, then this natural transition is no longer natural, we call it a bypass transition. So this subcritical, or this what we call linear stability analysis, has limited use, I would say. So now we go back to our original aim, that is derive an equation for Reynolds stresses, right? So for that we start with again this equation 8 without dropping the term, without dropping that bracketed term, that we have to retain. So we will go ahead, and so now we have considered equation 8, or the equation for fluctuating motion, and we proceed to derive an equation for Reynolds stresses. Okay. So we are not dropping this term here, we need this term. Okay, so bracket is there, it's minus of minus. So now what we do is, the first thing is we multiply this with another fluctuation, the way to derive what is called Reynolds stress equation. So we start with equation 8 and then we multiply throughout by another fluctuating velocity called uk prime. I and j are already used, so I take uk prime and ensemble average, yeah. So if I do that, I get uk prime dou ui prime by dou t average plus uj bar is the statistical value that comes out. So I get uk prime dou ui prime by dou xj ensemble average equal to minus 1 by rho uk prime dou p prime by dou xi. So now you see you are also seeing correlation of pressure and the velocities. You know, changing pressure field somewhere, fluctuating pressure is affecting the velocity fluctuations around. So we are seeing a correlation of these two, plus nu uk prime dou square ui prime by dou xj square average minus uj prime uk prime. The mean strain, that is dou ei bar by dou xj, is not affected by ensemble averaging, so it stays outside. Okay, and then this particular term, which is minus uj prime uk prime dou ui prime by dou xj average, and then minus of minus plus uj prime, sorry, uk prime uj prime dou ui prime by dou xj. So we have simply multiplied by uk prime throughout and ensemble averaged. Okay, any term that goes away here, the first term is a correlation, also the second term correlation term, the first term on the right hand side pressure and velocity correlation, again velocity correlation, velocity correlation. What about the last term? This is average of just the fluctuating quantity here, because the last one under the over bar is already a Reynolds stress, so this term is going away. But no need to panic, this was our Reynolds stresses, but upon multiplying by fluctuation and averaging, it is going away. No need to panic because it has come back in other forms. You see here, it has already come in a different term. Okay. Okay. So now we have one such equation here. Let's call this. I'll call this. Let's say star 1. Now there is a trick that we do here. One is that this I and k are now free indices. I takes value 1, 2 or 3, k takes value 1, 2 or 3. So I can rewrite this entire equation by interchanging I and k. Okay. So I comma k are free indices. So interchanging and rewriting the equation, we get one more equation here, simply rewriting by interchanging the I and k. So I get ui prime dou uk prime by dou t. It's not any other equation, it's the same equation. Whether I k value changes, when you expand it, it's going to be the same. Okay, that's the whole point of a free index. Plus j is used for divergence, j is repeated. Okay, so that remains the same. Here I get ui prime dou uk prime by dou xj average equal to minus 1 by rho. This is ui prime dou p prime by dou xk. K is replaced by I is replaced by k. Okay, let me know if I am making any mistake. I and k xj, ui prime dou p prime by dou xk, correct. Plus nu ui prime dou square uk prime by dou xj square minus uj prime ui prime dou uk bar by dou xj minus uj prime ui prime dou uk prime by dou xj average. let me call it an equation star 2. Okay, star 1 and star 2 are same if you expand. If you give a value I equal to 1 and k equal to 1, you expand it, you will get one equation. You get 6 equations here. So now all I have to do is add these two equations to get my Reynolds stress equation. Okay, we will see what happens. If I add star 1 plus star 2, adding the equation will yield. So here the equations are getting little intense, right? So make sure that we are following the right indices and all the rules properly. The equations has to be correct, then only you can model them. So now I have the two terms, writing ui prime dou uk prime by dou t plus uk prime dou ui prime by dou t, right? That's the first term, adding the first two terms. And then I have another term which is the convection term. So I am going to write it here itself, plus I have uj bar ui prime dou uk prime by dou xj, plus I have taken uj bar common out of the equation. So I get uk prime dou ui prime by dou xj average. Okay, the left hand side two parts equal to the right hand side. I get minus 1 by rho. I have uk prime dou p prime by dou xi. Okay, let me plus ui prime dou p prime by dou xk one of the terms, which is the pressure velocity correlation term. Adding them together. Now I add the viscous term, which is plus nu. I have uk prime dou square ui prime dou square uk prime by dou xj square average. The viscous term separates out, and then I have addition of these two terms, which is minus uj prime ui prime dou uk bar by dou xj minus uj prime uk prime dou ui bar by dou xj, those two terms. And then finally I have this minus of uj prime ui prime dou uk prime by dou xj minus uj prime uk prime dou ui prime by dou xj. Okay, so by adding these two equations I have got this. So some extra terms have come, and each of this term has a physical meaning. I'll come to that one. So this part and then this part. So before we start to rearrange, I have to do some tricks here to rearrange. First thing to note is that a pressure velocity correlation term has come, and you have a term here where mean strain dou ui bar by dou xj, mean strain is interacting with Reynolds stresses. Okay, and the last term is correlation of three velocity fluctuations. Okay, So the third order term that we discussed in chapter 1, statistical analysis, after variance I said, right, two signals can have same mean and variance, but they have higher order terms, the third order, fourth order, okay, like skewness, flatness. So you see this term has come, third order fluctuation, okay. So now if I rearrange the left hand side, this will take a little bit more time, but let's do only the left hand side part today now. So I can use if you look closely, this ui prime uk prime and then uk prime ui prime in the first term. I can use chain rule for products here and push the ui prime inside the differential operator, okay. So using product rule, I get the left hand side as dou by dou t of ui prime uk prime. Some of you were a bit upset that we lost the Reynolds stress term, but you see it has come back, okay, and we got it back in the form that we wanted, an unsteady rate of change of Reynolds stresses. That is why I said we are getting a transport equation for Reynolds stresses, and then no need to panic, we are getting an advective term also, the uj bar, again product rule, push the ui prime inside the differential operator. So I get dou by dou xj, divergence of your ui prime uk prime average, okay. So all the CFD enthusiasts should be very happy now. Now we are getting some general transport equation, okay. The left hand side is the easiest part. The right hand side will come up with more complicated terms, and each of them has a physical significance, okay.